Hi everybody, this video covers section 4.5, Introduction to Functions and Function Notation. In this lesson, we are going to talk about finding the domain and range of a relation or function, determine whether or not a relation is or is not a function, and introduce the concept of well-defined. We are going to use a concept called a vertical line test, which will help us determine whether or not a graph is a function or just a relation. And we're going to talk about a new way of expressing equations as a function using this thing called function notation. Okay, so what is a relation? Well, basically, a relation is nothing more than a set of ordered pairs. Now, it can be a finite set, like this relation here, or this relation here, or it can actually be an infinite set of ordered pairs, and in some cases it can even be a countably infinite set of ordered pairs. Now we have spent most of this semester working with linear equations, y equals mx plus b, and that actually is a relation, or it describes a relation, and from that equation we can come up with an infinite set of ordered pairs. As a matter of fact, we can come up with an uncountably infinite set of ordered pairs, and that would be our relation. However, in those cases, it's easier to express that relation as an equation or as a graph than it is a collection of ordered pairs because we simply just can't write them all. Well, here we have two relations. Here we have G. As you can see, it consists of 4 ordered pairs. And here we have F, and it consists of 6 ordered pairs. And notice that each relation has a name. This one's called G, this one's called F. Each of these ordered pairs has an X value and a Y value. The Y values are in black, the X values are in red. And these determine the domain and range of each relation. And the domain of a relation is the set of all first coordinates or the set of all the X values. And the range of a relation is the set of all second coordinates or of all the Y values in the relation. So for our first relation, G, the domain is going to be the set that contains the numbers 1, 2, 3, and 4. So here we are, that's the domain. And the range is all the Y values, which in this case is 2, 4, 6, and 8. All the Y values right here. For the next one, notice that we have only 3 different X values. 4 different X values. 1, 2, 3, and 4, even though we have 5 elements. And yes, I forgot the brace there. But there are still only 4 X values, so the domain is 1, 2, 3, and 4. And notice that for the range, there's only 3 different Y values. We have a 1, a 4, and a 9. Of course, the 4 is repeated here, and the 9 is repeated here. But as far as sets are concerned, we don't need to repeat them down here. 1, 4, 9 are still members of the range. And the last thing we need to talk about, well, not the last thing, but the next thing we need to talk about are functions. A function is a relation in which each domain has exactly one range element. So take a look at G. Every single X value has exactly one Y value. There is not an X value here which actually has 2 Y values. Or there's not another ordered pair that has a 2 and then some other number, or a 3 and some other number. As a consequence, we say that this relation is a function, and also we say that this relation is well defined. Why is it well defined? Because for every single X value that is defined in this relationship, there is exactly one Y value. As a consequence, this is a function. On the other hand, F is not a function. Why? Well, because take a look at the X value for 4. We have 2 Y values associated with this X value. As a consequence, we say that this relationship is not well defined at 4, because if you have an X, we are not sure which Y value we have. There's actually an ambiguity. The Y could be this one, the Y could be this one. As a consequence, this is not well defined, and this is not a function. More importantly, we can say that there are two ordered pairs with the same x value, and we can't have that. And to bring that home, this x value has two y values. As a consequence, it excludes f from being a function. Now, there is a rather cool visual way to determine whether or not a relation is or is not a function, and it works with the graph of a relation, whether that relation is finite or not finite. For example, here is a relation. This graph illustrates or is a pictorial representation of all the possible ordered pairs that fit this relationship. Notice once again, we could not write down all the ordered pairs because there's an infinite number of them that goes all the way to positive infinity and negative infinity. However, we can use the vertical line test to determine whether or not this relation is indeed a function or not. Now, if any vertical line is able to pass through 2 points, and this only has to happen once, then that graph does not represent a function. So here we have a vertical line. It hits the graph here, and it hits the graph here. That's 2 points. This is not a function. Check out this graph of our relation f. Now, and here's our vertical line. Now, notice if our vertical line was here, it would only hit 1 point. If it was here, it would not hit any points, and that's fine too. For x equals 2, it hits exactly 1 point. For x equals 3, it hits exactly 1 point. For x equals 5, it doesn't hit any points, which again is fine. But for x equals 7, it hits 2 points. And this only has to happen once to exclude this relation from being a function. So this vertical line test is a great visual way to identify relations and functions. And once again, it only has to hit 2 points once for that relation to be excluded from being a function. So these are not functions because, once again, the vertical line intersects at 2 points right here. And of course, for any value of x greater than -3, it's going to hit 2 points for this relationship, for this relation. Okay, now we need to talk about this idea behind a function. Now, we're familiar with an equation for a line. Here it is in slope-intercept form. Once again, the most intuitive way to express a line. And it also describes the ordered pairs between x and y. If you put in an x, you're going to get out a certain number, and that is an ordered pair. Now, in function notation, what we're going to do, and also this equation does represent a function. This will pass the vertical line test for any finite value of m. If m is infinite, well, then you have a vertical line, and that is not a function. However, what we can do is we can take this y and get rid of it and replace it with an f of x, with this f parenthesis x close parenthesis, and this is usually pronounced f of x. And then we're going to have this thing, which we call f of x is equal to mx plus b. And how would you read this? Well, we've just described the function. We are calling it f. The name of this function happens to be f. And the variable associated with this function is the independent variable. We're going to call this x. And this says that our function, which is named x, is defined as follows. You take x, you multiply it by m, add b to it, and that is going to be the output of the function. So f is the name of the function, and x is the input to the function. And if we replace x with a particular number, we're going to get an output, and that will be the output of the function. Okay, well, what the heck does all that mean in an example? Okay, well, suppose that we have this. Y is equal to 2x plus 1. We can write this in function notation as f of x, or f, which is a function of x, is equal to 2 times x plus 1. Okay, well, that's beautiful. What's so great about this? Well, let's suppose I wanted to evaluate this at x equals to 5. Well, in function notation, we would write that as f of 5, where we're just replacing x with 5. And this means to replace x with 5 and compute the function. And that's what we do here. F of 5 is going to be equal to 2 times x, which now is being replaced by 5, plus 1. And that will be equal to 11. 2 times 10 is, correction, 2 times 5 is 10. 10 plus 1 is 11. And that is the basic gist behind function notation. And what this produces for you is an ordered pair, where the x value is 5, and the y value, or the output of the function, is 11. Or we can write this as 5, comma, f of 5, where, again, this is basically equal to 11. We're just simply doing substitution. Here we have 11. 11 is equal to f of 5. We're just basically substituting that. Okay, so let's look at some of the examples that you might encounter in Hawks for this particular homework. And here's the first set of problems. Consider the following relation. And here we have it. We have negative 3, 2, 2, 1, 3, 7, 7, negative 2, 3, negative 4, 4, 4. So 1, 2, 3, 4, 5, 6 ordered pairs. And we want to determine the values in the domain and the range of this relation. Well, remember, the domain is all the x values, and that will be 3, negative 3, 2, 3, 7, 3, and 4. And there they are, 3, 2, 3, 4, and 7. The range will be all the y values, 2, 1, 7, negative 2, negative 4, and 4. And there they are, negative, and they don't need to be ordered, but I just do that for convenience. And there they are, negative 4, 2, 1, 2, 4, and 7. And that leads us to the next part, which is this relation a function? Well, notice here, it is a function if each x value is associated with exactly one y value. Well, here we have a 3, 7, and here we have a 3, negative 4. So we have one x value that has two corresponding y values, and that excludes this relation from being a function. So as a consequence, since we actually have, once again, a 3, 7 and a 3, negative 4, we have two ordered pairs with the same x value. This cannot be a function. Okay, example 2 is the vertical line test, and that should not be there right now, but it is, so we'll just deal with it. And the question here is, does this graph represent a function? Well, once again, here's our graph. It's actually a graph of a quadratic equation, which has the shape of a parabola. And here is our straight line test. And if you move this line anywhere along here, it's always going to hit the graph at exactly 1 point. So, yes, this does represent a function because it does indeed pass the vertical line test. If you kept on bringing it all the way down here, it will still hit the graph at least 1 point, although it's going to be way up yonder, and the same thing over here. Now we're going to be asked to determine the domain and range of the graph. And let's start with the domain. Now notice we have an arrow. This graph goes down here. We have an arrow going in this direction, and it's going to go on forever, which means we're going to be taking on x values forever and ever in this direction. Further, we have an arrow over here which keeps on going up and also keeps on going to the left. So it's going to include all the x values over and over and over here. That means that the domain is going to span all the real numbers. All the x values here will produce a y. And the range, I'll talk about the range in just a second. As a consequence, the domain is going to be all real numbers. Now for the range is going to be all the y values. Now notice that this equation, or this graph, has a minimum value. That minimum value happens to be negative 4. Okay, so it's never going to be any less than negative 4, but it's going to include negative 4. However, it's going to go all the way up to the infinities. So as a consequence, the range is going to be the half open interval from negative 4, including negative 4, all the way to infinity. And of course, since it's infinity, we can never reach infinity, so that gets associated with a parenthesis. So here, the domain is all real numbers, and the range is the half open interval from 4 to infinity. Okay, here is our next graph, and a question here is, does this represent a function? Well, the best way to determine that, and here the animation is correct, is by using the vertical line test. And notice right here, this vertical line crosses the graph at 2 points. It crosses it at -4 and -6. And anywhere within this range, it will cross the graph at more than 1 point. Actually, if we had the vertical line here, it would cross the graph at 3 points. And for it to be a function, it must intersect the graph at most 1 point. So this is not a function. It does not pass the vertical line test. However, even though it's a relation, we can still determine the domain and range for this particular graph. Notice that this graph never, or actually, I just realized that this is actually not correct. Because this, if you keep on going, if this keeps on going, it's going to include all these values over here. Actually, I even think Hawks has this one wrong. As a consequence, we could say that the domain, as a consequence, we probably could say that since this is going all the way up forever and ever and ever in that direction, we could say that this domain could cover all real numbers. And clearly the range does cover all real numbers because we're going all the way up this way in this direction, we're going all the way in that direction. So there we are. This part right here is not correct. Even Hawks got it wrong because I actually stole this from Hawks if we interpret that arrow correctly. And this should be all real numbers. Now, having said that, if you see this problem in Hawks, put this in because that's the answer they're looking for. Okay, moving on. Okay, here is a linear function. I'm sorry, it's a linear. It is the graph of a linear equation. And the question is, does this graph represent a function? And the answer is, yes, it does. Check out this vertical line. No matter where you move this vertical line, it will hit this straight line at exactly 1 point. So this is a function. Matter of fact, the only time this vertical line would not be a function is if you had the equation x is equal to some number, say -5. Because if you did, then the graph of that function is a straight line up and down at -5. Well, if I did it correctly. This is hard to do with my drawing pad. There it is, sort of. And if we move this vertical line, then obviously it would hit every single point in this function. More importantly, it would hit more than 1 point, and that that is enough to disqualify this from being a function. Okay, but back to our original problem. Okay, what is determine the domain and range of this graph? Okay, well, check it out. This graph expands since this line is going down forever in that direction, down and left, and this one's going up and right forever, the domain is going to be all real lines. Similarly, since this graph is going up forever and down forever, the range is going to be all real numbers. So for this particular case, for both cases, the range is all real numbers. The only time the range will never be all real numbers is if you have the case where y is equal to, say, 5. Well, then that graph is going to sit right here. That would be your graph. The domain would still be all real numbers, but the range would actually be equal to the point 5. And that would be if you had y is equal to 0 times x plus 5 for this particular case. It could be any other number. And so it occurs whenever you have a slope of 0 or a flat line. And of course that reduces to y equals 5. Oh, and I guess we're going to go to the next problem. Okay. This one is to consider the following graph, and this actually more is a 4.1 type exercise than it is, or at least this part is more of a 4.1 type exercise than it is a 4.5 type exercise. And we want to list the ordered pairs for each point. So look at A. A is at 1, 2, 3, 4, 5, 6, 7, 8 for in the x direction. 1, 2, 3 in the y direction, so its ordered pair is going to be 8, 3. For B, we have 1, 2, 3, 4, 5, 6 in the x direction, minus 1, 2, 3, 4 in the y direction. So this is 6 comma minus 4. For C, we have negative 1, 2, 3, 4, 5, 6, 7 in the x direction, and positive 5 in the y direction. So this is negative 7 comma 5. And then for D, we have negative 5, 6, 7 again in the x direction, and then negative 5, 6, 7, 8 in the y direction. This would be 7, negative 8. And if you, well, let me close out that parenthesis there. We need to do that. And that's what we have here. Okay, the next problem is to determine the domain and range of the graph. Well, the domain is going to be all the x values. Those are these. Well, I went too far down. Whoa, hang on, go back over there. Those are these values right here. And then the range, get a decent color here, is going to be all the y values, which are these values right here, 5 and negative 8. So what do you have? Well, for D, we have negative 7, 6, and 8. Negative 7, 6, and 8. And for the range, we have negative 8, negative 4, 3, and 5. And that brings us up to the next one, which is, hey, well, let's use the vertical line test to determine if the graph represents a function. All right, so there's our vertical line. Notice it hits when the vertical line sits at x equals negative 7, it hits 2 points in the relation. So therefore, this is not a function. And this brings us to our last example, and that is to practice using functional notation. So here you're given a function in functional notation, and here it is. Oh, didn't want to do that. We have let f of x be equal to 2x plus 3. And we want to evaluate the following. f of negative 5. Now remember, what we're going to do is we're going to take x here, and we're going to replace it with negative 5. Whatever is in, notice how when we have an x here, we have an x here. So whatever is in this parenthesis gets put into where the x is. So this is going to be equal 2 times, now we're going to, instead of x, we have negative 5 plus 3. And that, of course, will be equal to negative 10 plus 3, which is negative 7, which is what we have here. All right, next one's a little more interesting, or more annoying. I guess it's a question of perspective. Now we have f of a plus 5. How the heck do we handle this? Well, once again, we replace, wherever we see an x, we replace that with the quantity a plus 5, and we simplify and see what we get. So this is going to be equal to 2 times, instead of x, we're going to have a plus 5, and since this is basically one expression, we want to write this as parenthesis a plus 5, and then it's just the rest of the equation, or the rest of the expression, plus 3. Okay, now we want to simplify this, and to get rid of the grouping symbols. And in simplifying, the first thing we want to do is get rid of the grouping symbols, and we can get rid of these grouping symbols by multiplying 2 times a, which will give me 2a, plus 2 times positive 5, which will give me plus 10 plus 3. We can simplify this some more because we have like terms here. So this will give us 2a plus 13. And that would be your answer. And that is, oh, no, I have one more. And here we have f of x is equal to 5x cubed plus 7x. Well, that is a crazy function. That is a function. That is a pretty crazy function. We've never seen anything like that before. And we want to evaluate that at f of 1. Okay, and what that means is, once again, we are going to, wherever we see an x, we're going to replace it with a 1. So this is going to be equal to 5 times 1 raised to the 3rd power plus 7 times 1. Well, 1 raised to the third power, fortunately, is just 1 times 1 times 1. That's what that power means, which is equal to 1. Well, that's pretty convenient. So 5 times 1 cubed is just 5. 7 times 1 is just 7. This is equal to 12, which is what we have here. Okay, here's the next part. Evaluate f of a. Now, once again, this is our argument. The argument is the letter a. Wherever we see an f, or I'm sorry, whenever we see an x, we just simply replace it with an a. So this is going to be equal to 5, instead of x cubed, we're going to replace the x with an a cubed plus 7a, and that is it. Now notice what you've done. We started off with f as a function of x, and we have this. Here we have f as a function of a, and we have it now the exact same thing in terms of a. We actually call this a change of variables. It is a very useful term, or a very useful technique, not only in algebra, but also in calculus. And there you go. And that is pretty much all that I have as far as SciShow stuff is concerned. Give me a second and to get Hawks up and running, and we'll walk through a couple of practice problems in Hawks. Okay, so here we are in our standard Hawks setup. I have Hawks here, and I have OneNote on the right hand side. And let's go ahead and start practicing. So here's pre-certify, and this is the first set of problems that you're going to have. It's just like the our example, and unlike the example, I do believe I showed you plots. I don't remember. Well, anyways, in this one, you're given the collection of ordered pairs, and then they are graphed for you. And the first thing we need to do are determine the range and domains of each particular of this relation. Now, what you can do here is kind of scroll this down so you see the graph of all the points and then the domain and range. Now remember, the domain is all the x values. So we can go to each point and just write down their x coordinate. So here's a point. That x coordinate is -7. We'll put a -7 in. What? No, actually I need to get down here to where -7. The next one that's -3. The one next to that, there's one right next to that at -2. There's one at -1, whose x value is -1. I'm sorry. There's another x value at 3. And another x value at, okay, awesome. Now over here for range, for this point is all the way down. Now we look at all the y values. Now look at this point right here. It is -6. So we put a -6 here. Over here we have it's on the x-axis, so that's y is equal to 0. For the next one, we have +4. Then we have 1. Now this one's at +4, but we already have +4 in the set, so we don't need to include it again, but we need to include our last one, which is 6. So this is one of those cases where the domain and range don't have the same number of elements. However, this is a little different because here the range has fewer elements than the domain. For the cases when the relation was not a function, the domain had fewer elements than the range. But let's just go ahead first and see if we're right. We are correct, and we can move on to the next step. All right, and the question here is, does this relationship represent a function? Now remember, notice here that none of the x values are repeated. We have 3, -7, -2, -3, -1, and 8. So none of the x values are repeated. Further, if we imagine a vertical line, then the vertical line will either hit for any value of x. This vertical line will either hit no points whatsoever, or will hit at most 1 point. So as a consequence, since the x values are not repeated, since the vertical line will hit at most one point, this actually is indeed a function. Okay, the next collection of problems you will have is are graphs, and you'll be asked to determine whether or not that graph is a function or not. And of course, for this one, you need to imagine, you can't draw a vertical line, but you need to imagine a vertical line. And you'll notice here that if we do have a vertical line, it's going to hit the function at it's going to hit the graph at exactly one point, at any point, no matter what x is. Inside the graph, you can actually see it. But with the arrows, you can visualize that if you actually had a vertical line like at x equals 5 or at 10, it will intersect the graph at some point at some rather large value of y. So this is indeed a function because the vertical line will hit that graph at most one time. Well, will hit the graph at most once for any value of x. And there we go. Next, you're going to be asked to determine the domain and range of this particular graph. Now notice for the domain, this line is going up and to the left forever, which means it's going to include values of x that are negative 10, negative 20, all the way down to negative infinity. Further, the arrow to the right is going up and to the right forever. So it's eventually going to hit 5, 10, 100, all the way up to infinity. So the domain of this graph is all real numbers, and we will click all real numbers down here. Now for the range, now notice that this graph is going to go all the way up to infinity, but it never gets less than negative 5. However, it does include negative 5. So our answer for range will be bracket. Well, actually, what we need to do for this one is we need to bring up our keypad. Because remember, it's going to include negative 5, but we can never include infinity. So we're going to start at negative 5 with a bracket, and we're going to go all the way up to infinity. So you want to click this one right here. Then you can type in negative 5, comma, and then you can click on infinity right here, and that should be our answer. Whew, good, I'm glad that was right. I was going to lower there for a second. And let's move on to the next type of problem. Okay, this is the exact same type of problem as before, but since this one is not a function, we'll go through it. And notice that we had a vertical line here. It's going to hit this graph at 2 points, or in here and here. So this graph, which is a graph for a circle, is not a function. What about its domain and range? Well, notice the x values range from negative 1 all the way up to 5. Okay, so since the x values range from negative 1 to 5, its domain is going to be the closed interval, because it includes negative 1 and 5. It's going to be the closed interval from negative 1 to 5. Now, in terms of y values, it gets as low as negative 4 and as high as positive 2. So the range for the y values is going to be the closed interval from negative 4 to 2. Okay, so the next, and the rest of these that's the same type of problem as is that. Okay, here is a problem representing a linear equation or a linear function, because all linear equations are functions as long as you have a finite slope. Okay, so the first question here is this a function? Well, notice that if you actually had a vertical line, obviously over here it will hit the function once, but you can imagine that if you move the line to the left to negative 10, if you go up high enough, it's going to hit that function. It will never hit that function twice, or hit that graph twice. And the same thing over here. When x is equal to 10 or higher, at some point will hit the graph exactly once. So this is indeed a function. What about its domain and range? Well, as we've mentioned before, as this arrow increases, we're going to include more x values all the way up to infinity and all the way up to negative infinity in the y direction. So the domain is all real numbers. And also, as you can see with the arrows, this goes all the way up to infinity, all the way down to infinity in terms of y, so the range will also be all real numbers. Okay, so here's a problem where you actually have to plot down the ordered pairs and also determine whether this is a function or not. So let's go ahead and do that. First ordered pair for A is going to be -5, -7. For B, we have 5 down 4, so that's going to be 5, -4. 5, -4. For C, we're going to have 7, -8. Over 7, down 8. So that's 7, -8. And then for D, we have 7, +2. We have two ordered pairs with the same x value, so this is clearly not going to be a function. Let's see if we're right here, and we did that right. And then next part of this is to write down the domain and range. Well, once again, the domain is just a collection of all the x values. We have an x value of -5, comma. We have an x value of 5, comma. Just one comma, not two commas. And now we have an x value of 7 for C and D. That is the domain. For the range, we had to put in the y values. For A, the y value is -7, comma. For B, it is -4, comma. For D, we have for C, it is -8. And then for D, we have +2. Okay, and our last part is use the vertical line test to determine whether this graph is a function. Well, we're going to have to imagine a vertical line, and we can see that at any point for any x value, a vertical line will intersect the graph at most once until x becomes 7. Then that vertical line will hit D and it will intersect C. And since it intersects 2 points at x equals 7, even though that's the only value of x where that happens, it disqualifies this relation from being a function, so we click no. All right, and then the final types of problems that you're going to have are these problems right here, where we have to find the value, in this case, of f of 5. So we had the function f of x, which basically can be read as f of x, which is a function of x, is equal to 8 times x plus 6. And we want to compute f of 5. Once again, we replace the x with the 5. That'll be 8 times 5 plus 6. We always multiply first, so 8 times 5 is 40, plus 6, and this will be 46. All right, awesome. And now we have this funky sucker. We need to find the value of f of a minus 2. So we're going to replace f with x with a minus 2. And since we're replacing x with this expression, we need to use parentheses. So this is going to be 8 times the quantity a minus 2. So we have the parentheses there, plus 6. And then we can simplify this by first using the distributive property to get rid of the grouping symbols. 8 times a is 8a, but you can't do too much of that. 8 times negative 2 is negative 16. Bring down the plus 6. Simplify our like terms right here, and that will give us 8a minus, oh, and that should be a 6, not a 16. 8a minus 16 plus 6, which is minus 10. So let's see if I do that correctly. We would have 8a minus 10. And there you go. And those are the types of problems that you're going to encounter in this particular homework. As always, if you have any questions, please feel free to reach out to me. I'll be happy to help you in any way that I can. And this is Bob Boyle, signing off.